Hello, everyone. In this video, I will show you how to start Abacus that has been installed in your Windows PC, and use Abacus to create the model of a two-dimensional truss and analyze that truss using Abacus. And how to also I will show you how to use Abacus to interpret your results and visualize the results over here. So here in your Blackboard system, I have already attached a document where in which you should be able to follow the steps specified there to open Abacus as well as to create the model over here. So in this video, I'm gonna use this document to create the model and show you the results here. So firstly, as you can see here, and the first step is to open a Abacus. So if you have a Windows, you can go ahead search Abacus CAE, so that Abacus should be open in a few minutes, a few seconds, I would say. Okay, as you can see here, I have already opened my Abacus on my here. The next step, we can go ahead. Okay, I'm going to show you here. So next step, when there is, as you can see here, there is a window. I have the Abacus CAE 2023 installed on my computer, and here there are two options to create the model. With first one, and the standard explicit model. That's for, I think, for civil engineering, mechanical engineering fields, and I don't think we have any ECE student in our course. So I think we can just go ahead, click the standard explicit model, so that we have already entered the environment of the Abacus software. So there are a lot of buttons, a lot of menus here, but we will use some basic functions of this model. So firstly, let's go to the file on the left corner. So in the file, firstly, we'd better set the work directory. Right? So the work directory is a folder in your Windows system where all the files, including the model files as well as the result files or any log files, will be installed in that folder, so that in future, if you would like to visit those files, you can find where they are. So we select work directory. So as you can see here, when you click that button, there will be a window showing you how to set the work directory. The default one is the C drive, the time folder, but in my case, I would like to have a more desegregated one. Right? So in my computer, I have a OneDrive folder in my in the cloud. Right? So we have the CME here, online course. Can create a new one. So this is a tutorial one. So this is a tutorial. So I'm gonna use tutorial one in my course folder as a work directory. So everything related to this tutorial will be stored in that folder. So just click OK. So as you can see here, after I click OK, the new work directory is showing over here. So I click OK. So now I have already set up uh, the, the folder for me to uh, store any files related to this tutorial here. So next step, we can go ahead and follow the procedure over here. We create the geometry firstly, so we know this is a truss, 10 feet, 10 feet, and we have a diagonal member there. Diagonal member there. As you can see here, we can save as I save as a truss tutorial. Okay. So next step, we save everything as a truss tutorial. Truss can have the same name, truss tutorial. Tutorial. Okay. So we have already saved the model file. Nothing's here actually. The next step, we go ahead to create we'll use the sketch module to create the geometry. Right? We go back to here. As you can see here, there are um, different types of modulus over here. So the one we would like to use is the truss module, sketch modular. So we go to the sketch. We create the model. Create the sketch. So the sketch, we can have a name for the sketch. We can have the truss demo. So for the sketch, and approximate size does not matter actually over here. Continue. So there will be a great system over here for us to create the truss. So as you can see here, we enter the coordinates for the loads 1, 2, 3, 4. So we have the 0, 0, 120, 0 for node 4, 120, 120 for node 3, and then 0, 120 for number 2. So either way, that doesn't matter. So yeah, as you can see here, before we do the modeling, we would like to use a unit system here. As you can see here, the unit for length is inches. We convert the 10 feet to inches. Inches. Use the inch and the pounds. Inch and the pounds in this case. So enter the we just create we add a point. There is a isolate point here. So the first one is 0, 0. We enter the coordinate in the blank over here. So the first one is 0, 0. The second one is 120, 0. Use comma 0. The third one is 120, 120. And then the last one is 0, 120. We are done with the points. So we click the cancel procedure. So we can show all the points here. So as you can see here, in the screen, we have 4 pink points already created. The next step, we create the lines. So we have the lines so we have first line to this one, and the second line would be the diagonal one. So we click the escape one. So get the second one. Anytime when you wanted to stop the one, we can just go ahead click the escape button on your keyboard. So this is the geometry. This is the geometry. Right. And we are done with that geometry over here. So we click the done. So the sketch has already been created over here. So next step, when we go to part. So with the geometry, we can create the part. So we go back to part. So we create the part. It's a. I think we can go ahead um, add the sketch over here. So when you create a part, you wanted to select whether you wanted to create a three-dimensional problem, two-dimensional. It's a two-dimensional planar or axis metric. We will talk about axis later. The type should be deformable because you wanted to see the deformation, and the base feature should be wires because everything is online. It is nine geometry. Shear is for two-dimensional cases where you have areas or something. The wire over here is continue, and we can add the sketch over here. So we can add a sketch over here. So you can either well, from the model over here. You can add a sketch over here. I can add a sketch directly over here. You can either select the add sketch directly. So there is a menu, add. So we add the sketch here. We have already created the sketch here. So the sketch is pretty much like the CAD file. So it's like we import the CAD file into a CAE file. So we import the sketch. So reposition the entity, and that doesn't matter. We just keep the geometry here. So we just click done. And that's it. That's it. So we do not need the sections here. Just click done. So yeah, we have already created the model on the part. So part is pretty much like the geometry of the problem. Because when we use Truss analysis, the geometry we need is just three nines in this case, to represent the Truss members here. So we have the 1, 2, 3 members here. So we save the geometry. Next step, we need to, because when you do Truss analysis, when you formulate the stiffness matrix, you need, besides the geometry, you also need the material properties, such as the modulus of elasticity, as well as the cross-sectional information here, and the A, so you need the EA. So we need to enter another module. It's called property module. We go to the property module to input the modulus of elasticity. So we create the first button over here. So this is called material one. Click mechanical elastic. Is the elastic modulus. So the Young's modulus is given here. So it's 30 times 10⁶ order psi. So everything in pounds per square inch. So we have the Young's modulus, Poisson's ratio, and Poisson's ratio here doesn't matter, and you will see later. So we can just go ahead to use 0.3. Suggested in the tutorial. So we have already finished the definition of the material here. So next one, we need to give the cross-sectional area for this members. And click section, so that we define a section. It should be what type of beam section. So either type beam or truss. We define a truss. So we use the and after when you define the section, you need to tell what type of material your section will have. So the material has already been defined as material 1 in previous step. Right? So we just go ahead and input the cross-sectional area. Cross-sectional area is 2. Right? Is 2. Enter 2 here. So we click OK. So we have already defined the material and the cross-sectional area. And next one, we just assign. We defined them in the system, but the system hasn't yet received any information for this geometry. We need to associate. We need to connect the section we have already defined to the members. Right? So next step, we click the assign section. We assign the 3 section with the property we have already defined. Right? We select all of them. You can make a selection from right to left here. So you click OK. I've already select all of them and we assign the section 1. We have already defined the section 1 to all of them. Then it's done. It's done. So, so we're done with the module of property. So we click OK. We can save everything here. So next one, we go to go to the assembly. Assembly, because this for this case we have only one part, but in future you may have multiple parts. You wanted to combine multiple parts, and the different part may have different element types, such as you may have beam elements for one part and truss element for the other part, or the plate element for one part, beam element for another part. So you need to assemble them. So next step, go to assembly here. Before you do any assembly, actually in the model space, there is nothing. Nothing. So we need to click the instance. We click instance. An instance is like is one copy of your part. Right? You may have. So we create instance. There is only one part here, so we just select an auto, create part instance from parts, and the instance type. You can select either dependent or independent. That doesn't matter in this case. Say dependent. The modular just use dependent. Just click OK. So the data has already been transferred from other place to the model space here. So we click OK. Assembly is done. And the step. Okay, next time we create a step. As long as we have the model, we create a step. The step should be a initial static general step. We accept everything as default. Right? Create step 1 would be after the initial. The initial is the start point. Step 1 would be a static general analysis. Right? Continue. Just click OK. We do not need to do any changes here since everything is pretty simple for this tutorial. Interaction, there is no interactions. We have only one part. Interaction are all you only use to collect different parts. Since we have only one part, we skip this. Next time we go to the load, we define the load. So firstly, we apply the force and the node 0, 0, right? And the force is 10,000 pounds. Then we apply the constraints, right? We apply the load. So this is a node in step 1. Should be a concentrated force. So then if you check the the guidelines instruction at the bottom of the main window over here. So Abaqus asks us to select points for the load. So the load will be the 0, 0 point. Select them, and then there is a new window comes up. So we need to apply a load. The load is a vertical load, so and it's 0 in x direction and minus 10,000 in the vertical direction, in the y direction. And it's so this is the model with the load applied to that point. So next step, we create the boundary conditions. We would like to restrain and note all the loads at other ends of the chart element. There should be displacement and rotation in this case. Continue. We select the regions. We select all of them. So we select the first one. If you would like to do multiple selection, you can press the shift button over here. So select the second one, select the third one. So all of the three have been selected. We click down and we check the. So as you can see here, all of them are pinned. So we just U1 and U2, both and X and Y directions are constrained. Okay, so they are constrained over here. We click save, everything is saved. So up to here, we have already applied the force. We have already applied the boundary conditions. So we can go to the mesh now. Go to the mesh. The mesh means that we assign the element types and the element sizes to the geometry we have already over here. So firstly, we need to tell the sizes or the numbers of elements for each truss member here. So as you can see here, for the mesh, firstly we do the seeding. Secondly, we do the mesh, and we need that tell the element type. So this first one, seed is for element size. Second one is for element type. As long as we define this element size and the element type, we can do the mesh. So 3 steps. So firstly, we do the seeding, and we seed a part instance or seed the edges, or you can select from the drop menus here. We seed edges. Dependent parties cannot be added or assigned a mesh attribute. Okay, we make it independent. That's okay. We can go to the model database on the left side. So we'll go to the assembly here. Have the part 1 assembly selected. Make it as the independent. So now we can see the edges. We select all of them, and now we would like to have only one element for one truss member. So we seed by number. So each of them will have only one member. So as you can see, you can tell from something has already some changes occurred over here, right? You can see the loads at the end of the truss members. We are done with the assignment of the element sizes here. Right? The next step, we need to tell the element type. We can use the drop menu over here. So element type, select all the region, tell the type of the element. So the type of element will be standard. There's the truss. There is truss. We do not do any changes here. We just select the truss. As you select the truss, there will be a name for the truss member. It's a 2D T2 D2. It's a two-node linear 2D truss. Okay, so we click OK. So we are done with the selection and the assignment of the truss types. Truss types here. Okay, so as long as we are done with the truss types, on the element types, element sizes, we can do the mesh the instance. Okay, so there is a window showing whether we are okay to mesh the party instance. We click yes. So it's meshed. As long as it's meshed, the color of the model changes. Changes to light blue over here. So nice green or light blue. So save it. So up to here, we are done with the modeling. We are done with the modeling. We have already applied the force, boundary conditions. We have already assign the element numbers and types to the different members over here. So we should be able to analyze it. We go to job module. Go to job module, create a job. Job is a task for the Abaqus to do the analysis. Right? We may use some special name for the job, or we just keep it as job one. We continue. We do not do any changes for the analysis procedure or analysis method here. Just click OK. So we're done. As you can see here, bottom here, so the job has already been created. So we can go back to the job manager over here. We go to the job manager here. You see the job one is created for model one, and so that's the model we created. And we would like to have a full analysis for the model, and the analysis is not yet done. It's not yet done. So in this case, we can just click submit. And an Abaqus will start the analysis. So the status tell you it is running. It is running. Now, or you can monitor the analysis. Okay. Yeah, for this type of analysis, it is done in a few seconds. So now, as long as the status becomes completed, you can check the result. Click the result. So we have ready and entered the visualization module over here. So this is the model with the analysis results. So we should be able to change. Firstly, where we should be able to change the font size. Okay, we change the viewports and animation notation manager reports. Okay, edit annotation. Oh, so what's that? Annotation view annotation options. Do you have this? First annotation options. We can change the font size. Yeah, if you would like to have a larger font size, we can have a larger font size. Legend, title block, and change all the font sizes or any. Yeah, and that's up to you. You may change it. Or if you want to keep the defaulted one, we can keep the defaulted one. Or we can change the graphic background. So here we have the gradient background over here. So if you like to have a pure solid, for example, if you like to have a white background or black background. You can change that too. We can change it to black. So now everything has already been changed to black and to white. White one. And it is good for presentation if you have a white blackboard, black background, other than the gradient background over here. So now next step, we can show the element labels. We can show the element labels, right? Element labels. So display options, entity, up here to the view options. No, up here, view. Okay, let me double check. Yeah, show. That's option is common. Common. We have the options. It's not here. The options is not here. Easy. We have already checked that. Oh, no, that option, so do not night image. Oh, so over here, it should not be here. That's common. Yeah. We check that. Check this. We check this. Interesting. Or we can just go ahead. Common options over here. It's over here. So sometimes options. Okay. Yeah, that's on the drop menu here. Or we can just go ahead check here. Common options. We can show the levels for the load and the element. So this is for the element level. For the load level, we can show. I can change the colors since the element. It's too light. We cannot see it clearly. We can change the color to black. So those are the node numbers. Or we can show the elemental lab different color. Maybe we use the black one too. So those are the elemental tabs. So we have the element 1, 2, 3, and node numbers. So those are some information we can show here. Then we can okay, the element lab was black, node number was red. Okay, we change that. That's red. So those are the different levels over here. So next step, we show the deformed shapes or undeformed shapes. We go to plot. This is undeformed shape. If we click the deformed shape, this will show the deformed shape. And then we can also show the contours. Yeah. So we show the stresses here. Stresses. So sigma S11, that's the axial stress. That's axial stress. Sigma 11, we can plot contours, deformed or undeformed. We can do either. Show that. So this is a recesses results. We can recheck the results field output. This is the recess. We can use the result option here, and we don't want to do that. The average, we can check the average. So those are the recess results. We can change it to S11. So this is S11. So we can have the maximum. We can show the stresses for different members over here, different members here. And then we can also copy figures to clipboard. For example, you can either print, you can print the colored to a file. For example, file name, that's the stress, Abaqus stress. And you can save the name of the Abaqus stress, and this file will be saved to your work directory. Will be saved to your work directory. You click OK. So this has already been saved to your work directory, or you can just go ahead and copy it with Control C, copy it to a Windows file or Word file. So this is a stress. You can also show the displacement. So for example, if we would like to know the displacement, we can go ahead, we can go to, oops. We can go to the report. We report the field output. If we would like to output the loader, the loader, each unique loader displacement, U1 and U2. So the displacement in 1 and 2 directions to a data file. I click the data file, so it can be saved to an Abaqus report over here. So everything will be reported over there. So we click OK. So the displacements of all the loads has already been saved. Or we can also save the S11, the result. We can show all the Abaqus stresses. We go to the report, we show the stresses, we select the stresses. So I want to show the S11, click OK. Everything has already been saved to the Abaqus report file. So where is that? I saved that in my online course tutorial one. So everything, all the files for this tutorial has already been saved in my work directory, as you can see here. And the model or the result file, we can open the result file, as you can see here. So result file, we have the displacement for node 1, the 2, and then the stresses. The stresses should be for element. So we'd better change the report here a little bit. I just go ahead and delete the file, and so we change it. Because the stress makes more sense for element. So we uncheck for the element. We select the an integration point or elements or element. No, element. Base, not element. Base. Just click this. Okay, so this is not for. Okay, just go ahead and use the stress. Anyway, right there. Elemental lab. Okay. Position variable, centroid. I would just output the centroid. Looks like we need to re-input the result. So report the result. Just select the centroid for the stresses. This makes more sense here. Okay. Okay. So we need to output the displacement firstly, and then just output them in different files. So now we have everything in that file. Now so we have the displacement, and we have the displacement here for each of the load, and we have the stresses for each of the element. And let's compare with okay, we have the same values. We have the same values here. Same values as in the file. Right? So the only difference is that the nodal numbers may be a little bit different here, but as long as we have the information, we should have the same result. So that's how we analyze this result and this result. So there are other so if some of you are interested in axial forces, we may be able to output the axial forces too. Let's see whether we can have the force. Okay, reaction force. So the other forces are not recorded here. Point loader. We can also output the point load, the string energy, stress component. Okay, let's go back to the step. Now we can also specify whether we can have the internal forces. The internal forces, example, concentrated forces and reactions. We have the section forces and moments. Let's say whether we can output the section forces and the moments. In this case, the body forces, and then we redo the submit the project. Okay, we have already completed the analysis. Go back to visualization. We import the result again. Let's say whether we can have any section force. Unfortunately, for truss element, we cannot have the section forces output. So the only thing we can have is the stress. But then, as long as we have the for section, we should be able to find out the axial forces for this problem. Okay, I think that's all for this tutorial. Good luck for your try, and thank you.